Greetings. I hope all of you are doing great. Now, today we're going to take a look at the Krebs cycle, and we're going to make this as simple as possible so we can understand it and appreciate the processes and the changes that are taking place within the Krebs cycle. So just walk with me a little bit. Now, before I jump into the cycle, I want to take a look at some key points. Now, the first thing I want to remind you about is that the Krebs cycle is also called the citric acid cycle or the TCA cycle. And TCA is the abbreviation for tricarboxylic acid. Now, the next point I want to point out is that the Krebs cycle takes place in the matrix of the mitochondria. It is also important to note that the purpose of the Krebs cycle is really to change acetyl-CoA into NADH. And NADH, they carry a lot of electrons, which are high energy, and they are used in the ETC to produce a surge of ATP. Another point to note here is that there are 8 enzymatic steps throughout the Krebs cycle, and I'm going to make reference to those steps as I go through the cycle itself. Another point here to remember is that the substances that are involved in the cycle, they are acidic in nature. And again, I'm going to use that to make reference in terms of our H plus ions that are produced throughout the cycle as well. All right, so let's now dive into the cycling. Now, to have a cycle, there must be a continuous path. So I'm using a circle. I mean, you can use a square. It doesn't matter as long as it's showing a continuous path and you have the correct compounds in their appropriate places. Now, before this cycle can take place, it will use some substances that were produced from a previous phase or stage of respiration. The first stage of respiration is glycolysis. And glycolysis produces pyruvate molecules that are used in the Krebs cycle. Now, so the Krebs cycle requires pyruvate, but pyruvate must be converted into acetyl-CoA. Now, I want to make a note right here is that pyruvate is a 3-carbon molecule and acetyl-CoA is a 2-carbon molecule. And once the acetyl-CoA is formed, it will be taken into the cycle to start the cycle itself. Now, typically, you'll notice that the cycle starts from the top of the circle, but it doesn't matter where you start, right? As long as you have the compounds in the appropriate places. And so you could put the acetyl-CoA going in from the top, but make sure that you have the correct lineup of the compounds. Now, the only thing I want you to think about at this very moment is the number of carbon that are present in each molecule. And that's the only thing I want to look at. And the reason I'm going to do that because I want to approach the cycle in terms of how the body forms or similar to the body itself. So in other words, what I'm going to do, I'm going to develop a skeleton, and from the skeleton, I'm going to put some flesh onto it, and then I put a layer of skin. So I'm going to put layers on top of layers until we have a complete cycle. All right, I think that approach may be one of the easiest way to look at it. Now, again, look only at the number of carbon present in the molecules. And so pyruvate is a 3-carbon molecule, turns into a 2-carbon molecule. And then this will enter the Krebs cycle. And again, just to point it out that only the circular part is the cycle. Pyruvate turning into acetyl-CoA is not a part of the cycle. That is the precursor for the cycle to take place. All right, so it's not in the cyclic part. Now, the 2-carbon molecule right here will merge with a 4-carbon molecule, okay? Now, this merger will produce a 6-carbon molecule. And so 2 plus 4 is 6. Now, this 6-carbon molecule will further form into another 6-carbon molecule. And we'll talk about the difference between both. And then the 6-carbon molecule will turn into a 5-carbon molecule. There's only one 5-carbon molecule, and then this 5-carbon molecule will turn into a 4-carbon molecule. Now it turns out that this 4-carbon molecule will make 3 other 4-carbon molecules. And so we'll have 1, 2, 3. And so in total, of the 4-carbon molecule that we started out with and the one that was produced from the 5-carbon, we have a total of 5 4-carbon molecules. So I'm going to show you a summary of all these carbon molecules on the left of your screen, and it will come up right now. And we call these intermediates because all these compounds that are formed within the cycle, they are called intermediates. And so within the cycle, we only have 2 6-carbon molecules. So notice 1, 2 here. We only have 1 5-carbon molecule, if you make a note of it, on to the right. And then we have 4, for the 4-carbon molecules, we only have 5 of those. All right, so please remember these numbers, 2, 1, 5 in terms of the number of carbon molecules that are produced, 6-carbon molecule, 5-carbon molecule, and 4-carbon molecules. All right, so there are 2, 1, 5 in that specific order. All right, so now we covered that. What is important for us to look at right now is what is happening to these carbon molecules. And I want to make a note right here, if you notice it as well, that at various points you have a reduction in the number of carbon atoms within the compound or molecule. Take it, for example, from the pyruvate into acetyl-CoA, the number of carbon reduces from 3 into 2, so there's a missing carbon, and we must account for that carbon. And so once a carbon is missing throughout the cycle, it means that carbon dioxide is formed. So anywhere you see a reduction in carbon, please put a carbon dioxide. So starting from the pyruvate to the acetyl-CoA, a carbon is missing, so we can absolutely put a carbon dioxide right here. So this accounts for the missing carbon. If you look over to the 6-carbon into the 5-carbon, again, it's a reduction by 1 carbon, so therefore carbon dioxide is formed at that point as well. Moving from the 5-carbon into the 4-carbon, yes, absolutely, there's a missing carbon as well. And so therefore we need a carbon dioxide at this point. All right, how do you think that you're doing? I hope you're doing good. Now, again, you can always stop and pause and make sure that you understand what is happening here. All right, so now is this is just the skeleton with just a small amount of flesh onto it. So we're going to add some more flesh. All right, now the next thing that I want to look at, right, is in terms of chemical reactions. Now, chemical reactions occur when bonds are broken and bonds are formed. So once you're breaking and forming bonds, electrons are involved. In fact, some of the electrons are set free. And so we'll have some free electrons produced, but if you think about it, if you have free electrons roaming in your body, they can cause unwanted reactions because electrons are negative in charge, negative in terms of their charges, and they will react with positive substances. So it turns out now that our bodies have some collectors of electrons. We call them electron carriers. So they collect the electrons and carry them to the electron transport chain, which is ETC, the final stage of respiration. So take it for example, from 3-carbon to the 2-carbon, a bond was broken. That is why we produce carbon dioxide. So what will happen here, we have a electron carrier come in play and pick up the free electrons. The electron carrier is in the form of NAD+, and they pick up electron and turn into NADH. Now you may be wondering now, why plus a positive hydrogen ion? Why there is H plus ion at the end? Now I'm going to tell you where this comes from. Now, remember I said that the substances involved in the cycle, they are acidic in nature. For example, pyruvate is also called pyruvic acid. Once acids react, they will release or dissipate H plus ions. Matter of fact, by very nature, it is the H plus ions that make acid acidic. All right, and so the bonds are broken, the free electrons are released, so they pick up by the positive NAD plus, and then because of the acidic nature of the substances, they release H plus ions. All right, let's look at other locations in the cycle to see if we need our electron carriers. And remember looking for the locations where bonds are broken. And so if you notice from the 6 carbon to 5 carbon, absolutely a bond was broken here. So definitely we need our NAD plus turn into NADH. And again, from the very nature of the substances, they will produce H plus ions. Now, from the 5 carbon to the 4 carbon, yes, a bond was broken. So therefore, we need, again, our electron carrier, all right, to pick up these free electrons. And if you notice, again, in the cycle, anyway, so the carbon dioxide produced, you know that you must have electron carrier, because the produced carbon dioxide, we break bonds. Now, there are 2 other locations that may be difficult to identify where we need electron carriers. But I'm going to give you a little hint in terms of how to remember them. These are the 2 locations. And so the first location where you need an electron carrier is at the second 4 carbon molecule. Now, here it will be a special electron carrier in the form of FAD, and it will turn into FADH2. Now, I want you to notice something here, all right, which is by no means any chemical association at all, but the second 4 carbon molecule requires FAD that will turn into FADH2. So I just use the 2 after the H to remind me that it is produced after the second 4 carbon molecule. Again, there's no chemical association with H2 and the second carbon, but just a means of remembering where it is needed. Now, the other electron carrier is needed when you produce the final 4 carbon molecule. So the production of this 4 carbon molecule, again, is a preparation to receive the acetyl-CoA, and so therefore electrons will be set free in this regard, and so at this point you will need an electron carrier, and so therefore NAD plus will convert into NADH and hydrogen ion. I want you to quickly notice that within the cycle itself you have only 3 NADH, okay, and also 3 H plus ions and only 1 FADH2, okay, just to make a note. Now, you'll also get a little bit more understanding when I look at the enzymes, why at these 2 locations, why we have bond breaking taking place. Again, it is not easy to see by just looking at the 4 carbon like that. Seeing the structure will make it more clearer, because the structure will show you where the H plus or the H hydrogen ions are actually removed from the very structures. All right, so let's put on some more flesh into this. The flesh we're going to add to this is in the form of naming the molecules that are produced in the cycle. Again, we call them intermediates. The first intermediate that is formed in the cycle, it is this 6 carbon molecule, and it is called citrate. It is also called citric acid. Again, it is acidic. It turns out now that the citrate will form into isocitrate, okay? And then we'll jump into the 5 carbon molecule. This one have a longer name, and so this one is alpha ketoglutarate. All right, so alpha ketoglutarate is the only 5 carbon molecule that is formed, and so you can also kind of remember, associate a name with thus the only 5 carbon molecule. All right, for the first 4 carbon molecule, well, there's no association necessarily, but this is a start of the set of 4 carbon molecules. And so here it will be succinyl CoA. So succinyl CoA If you notice, it is the start of the four carbon molecules, and also at the end of the four carbon molecule, it will join to another CoA, which is coming from acetyl CoA. Okay, so the four carbons, they are associated with the coenzyme A at the start and at the end, just to make a note of that. All right, so here now, succinyl CoA will form into succinate. All right, and so succinate is the second four carbon molecule. Then the other four carbon molecule here will be fumarate. And then fumarate will form into malate. And then malate will form into the final four carbon molecule, is called oxaloacetate. Okay, so again, you can just slow it down and pronounce this name, which is oxaloacetate. Okay, so oxaloacetate is our final four carbon molecules. A very important four carbon molecule, because it is the molecule that will combine with the acetyl CoA. So again, remember, the first four carbon molecule is associated with CoA, all right, and the final four carbon molecule will now rejoin to a coenzyme, all right, which is acetyl CoA. All right, and so there we have it, really meaty now. We getting meaty. Now, can we add some more flesh to this? Make it really nice and juicy. Now, let's add some more flesh here. But the flesh we're going to add here now is really to add the names of the enzymes that are involved. Because remember I said, in the first part, that it is an enzymatic reaction. And each substance that is produced with the aid of an enzyme. All right. In fact, the number of intermediates equal to the number of enzymes required, and also equal to the number of steps. All right, so let's just quickly put in our first enzyme. And so the first enzyme here will be producing citrate. So this one is called citrase synthase. Now our second compound that is formed right here is isocitrate. And so it's a kind of a funny enzyme, because it's not associated necessarily with the name of the substance that is formed. But this one here is aconitase. So aconitase is the second enzyme that is produced here, that used to form isocitrate. And then now from our 6 carbon into our 5 carbon. And I want you to notice something here, that moving from 6 to 5, that there's a breaking in bonds, and we actually lose hydrogen. And so therefore this enzyme right here is called isocitrate, coming from the citrate. And what the last part of the name of the enzyme is dehydrogenase. And notice it, dehydrogenase. So it is D, which is removing hydrogen. And that is why the hydrogen is being removed and become H+, because from the acid, the H+ ion has been removed. And that's why that enzyme is called isocitrate dehydrogenase. Now, moving into a 5 carbon to a 4 carbon, I want you to notice something again, that this is a breaking of bonds, and we have H+ ions that is formed. So this should tell you the name of the enzyme coming up here. And this one is called the ifoketoglutarate dehydrogenase, because again, we remove an hydrogen atom. All right, and see the H+ ion that was removed from the acidic part of the substance. All right, so notice the names are pretty much easy to remember, with the exception of aconitase. All right, let's move on to our first 4 carbon molecule into our second 4 carbon molecule. And for the 4 carbon molecules, I'm going to kind of give you a little rule in how to kind of remember the name of the enzyme. Now, I want to think about we're coming from to where you're going. So in most of the cases, if you notice, in the 6 and the 5 carbon molecules, they're actually based upon the name of what is breaking down. But from the 4 carbon, it's a little bit different. So for example, succinyl CoA, the enzyme that will be here is succinyl-CoA synthetase. Notice the name here, synthetase, is different from synthase. Now, synthase, we're building the citrate, but in the synthetase is actually breaking down the succinyl-CoA. All right? And so succinate was formed based on this. So it's kind of opposite. If you notice, it's actually from where it's coming from and not to where it's actually going in terms of a cycle. So it's kind of different with the 4-carbon molecules if you realize that trend. All right, let's look at the other enzyme and you may see the trend that I'm talking about. All right, so we're coming from succinate into fumarate. And so the enzyme that will be here now is succinate dehydrogenase. Again, because here an hydrogen atom will be removed, all right, or hydrogen atoms will be removed from the 4-carbon into the other 4-carbon, which is succinate, into fumarate. And if you remove hydrogen, you need an electron carrier. And this reason, again, we have our FAD turn into a FADH2, if you notice that. All right? Now let's move into fumarate into malate. Again, notice the name that's going to come right here. This one is called fumarate. So the name is always associated to the compound that is actually coming from. All right, so right here now, the fumarase will form malate from fumarate. And then now for the final one, I'm sure that you're trying to predict the name of this one, all right? But let's see how good you did. All right, so this one is called maltate dehydrogenase. Again, once you see the NAD plus and the H plus ion, it therefore means that hydrogen or H plus ions were actually removed. All right, and so definitely, if you notice, the names of the enzymes also indicate the processes that are actually taking place. Notice wherever you see electron carriers, notice what you see there. You see dehydrogenase. Everywhere you see the production of substance with I electrons in them, or simple put, electron carriers, you will have a dehydrogenase enzymes there, because H plus ions are removed at those locations. So kind of easy to remember like that. Again, the last thing I want to show you with this, the second to last thing I want to show you with this cycle is a number of steps. The number of steps are indicated by the number of enzymes or the number of intermediates that are there. So let's quickly just number them real quick. So the first one again is the citrate. So definitely citrate synthase will be the first enzyme. All right, so great. So notice to see all our numbers here, 1 to 8, and so there are 8 steps, and we actually say there are 8 enzymatic steps. All right, and so the next thing I want to show you right here is where you produce ATP, and ATP is produced at our first carbon molecule. Right, so it's a burst of energy that is produced there. It turns out, of all this work, you only produce 1 ATP. This is really a task. But the most important thing is not necessarily ATP that is produced at this point, but the NADH that are produced that will be taken to the ETC to produce a lot of ATP. So all this work that is going into the Krebs cycle is just for the production of NADH that are needed in the ETC, and only 1 molecule of ATP and 1 molecule of GTP produced per cycle. All right, so what I want to jump into real quick is a kind of a summary and summative need. I think you really need this. And what I want to look at is the output that we get from the cycle and also the output per glucose molecule. And the way of this is just to let you know that coming from glycolysis, there are 2 pyruvates. And so each cycle only treat one pyruvate molecule. So therefore, there are two Krebs cycle or two Krebs cycles for each glucose molecule. And so per cycle will be half of the total amount produced per glucose molecule. All right, so let's look in terms of our NADH. And so NADH, we only have 3 of those produced in the cycle itself, not the precursor of the cycle, but only in the cycle we have 3 NADH. And wherever you have NADH, you also have H plus ions, so therefore you have 3 H plus ions as well. And NADH is the abbreviation for adenine dinucleotide. Also, we have 1FADH2. Remember, we talk about that, and this is flavin adenine dinucleotide. We also produce 2 carbon molecules, 2 carbon dioxide molecules, I should say, from the 2 missing carbons. We also produce 1 GTP, and GTP is guanosine triphosphate, and we produce 1 ATP molecule, which is adenosine triphosphate. Again, per glucose molecule will be twice per for those per cycle, because again there are 2 cycles, one for each pyruvate molecule that were produced in glycolysis. And so, of course, we're going to double up all these numbers. So we're going to have 6 NADH and 6 H plus ions. We are also going to have 2 FADH2. We will have 4 CO2 as per glucose molecule. We will have 2 GTP, and we have 2 ATP. So this is the sum of the output from the cycle and also per glucose molecules. I hope this was really helpful for you. Now, I really want to tell you that I appreciate you watching all my lessons and even watching this lesson in particular. All right, and I just want to tell you that life is really a cycle. And I'll quickly remind you that the position that you're in right now, someone else in the future will be in that same position. So in the time being, appreciate life for what it is, enjoy your life, do your best at it, and just cherish every moment that you can. All right, so anyway, have a safe and blessed day, be encouraged, and I will see you soon.